In our second example, we have a slightly more complicated circuit. We've got two resistors kind of out on their own, wired in series, R1 and R5, and three resistors wired in parallel in the middle. So once again, we will set up a VIRP table, and we will enter in the known values. So we have 5 resistors here, and we label their resistances accordingly, and we put in the 50 volts, which is the total voltage. Our general rule is to start with the parallel sections first, seeing as that an electron has to go through R1 and R5 and the entire parallel section. Those three as a whole are wired in series. So we'll analyze the parallel section first. And if I combine those using the inverse equation, I will find that the total resistance of those three is 1.55. Well, the 1.55 is the resistance of that parallel section, and that entire section is in series with the 7 and the 2. So I go ahead and I add the 7 and the 2 to that, and I get a total resistance for the entire circuit of 10.55. So I can enter that in my total resistance in my VIRP table, and utilizing Ohm's law, since I know that V equals IR, and the voltage is 50, and the resistance is 10.55, if I divide 50 by 10.55, I find that the current is 4.74. Now I recommend on the diagram itself, you draw little arrows representing that current. So I know 4.74 amps comes out of the negative terminal of the battery, must pass through R1. It's going to split through R2, R3, and R4, but it will come back together and be 4.74 as it passes back to the positive terminal of the battery, therefore passing through the fifth resistor or the 2 ohm resistor. So because R1 and R5 are on what we would call like main highways or main pipelines, sections where every electron must go through, there's no choice but to go through them, they get the full current. So I can apply the full 4.74 to R1 and R5 because there is no other option around them. In order to figure out the parallel section, we again need to apply Kirchhoff's rule. So we know that 4.74 amps is going to flow into that section, and we're going to set up our proportions. So 9 over 9 for the first, 9 over 3 for the second, 9 over 5 for the third. We're utilizing 9 since it's the highest resistor. Those come out to ratios of 1, 3, and 1.8 respectively. I'm going to apply X to represent the current in each of those branches, and I know when I add up the current in those 3 branches, it must equal the total of 4.74. I can just apply my algebra and solve and determine that X equals 0.82. So what that tells me is that 0.82 amps will pass through the 9 ohm resistor because its ratio is 1 times X. To find the second branch, well, that is 3 times X, so 3 times 0.82 gives me 2.46 amps. And to find the last, it's 1.8 times X, which is 0.82. So that must be 1.48 amps. So now I've figured out how that 4.74 splits, and I can apply those individual values that I just calculated into my current column in my VIRP table. I'm through most of the difficult portion of this problem. Now I simply have to use Ohm's law, V equals IR. And if I multiply each I by each R, you will find that you get the following voltages. Once again, if you notice, resistors 2, 3, and 4, aside from some slight rounding differences, they all come out to about 7.4 volts, which makes sense because parallel resistors all experience the same voltage. So it lines up with the concepts we know are true, which tells us we're probably on the right track. Now I have VI and R. I can utilize any equation for power that I'd like. P equals IV, P equals I squared R, or P equals V squared over R. I used IV, and I can calculate all of my powers. To check, we'll clean some things up here again. To double check, we need to make sure that our voltage for any singular pathway adds up to our total voltage. So pathway 1, which is one option, will bring me through R1, R2, and R5. And if I take a look at R1, R2, and R5, and I add them together, I will find that that adds up to 50 volts. So I know that pathway 1 checks out. If instead I want to take pathway 2, and that brings me through R1, R3, and R5, I can look at R1, R3, and R5, and once again, it adds up to my total of 50. And if I want to take my third possible pathway, that brings me through R1, R4, and R5. If I find those in my table, once again, those all add up to 50 volts. So my little self-check has demonstrated that I can assume I'm correct with about 99% accuracy. Always do that self-check for complex circuits, and you should know whether you did the problem correctly.